Hello and welcome to the final installment of this long as heck series on the integral over powers of the tangent function. We're finally getting to the end. I'm finally going to prove what it's actually equal to, how it's related to the integrals of powers of the natural logarithm that we've done in the last few videos, and how it actually is related to the Euler numbers, which are the coefficients of the Taylor series for hyperbolic, secant, and regular secant functions, and that will all come into fruition today. It's a beautiful connection. We're going to need the beta function, the gamma function, U substitution. We're going to need to know Taylor series. It's going to be great. It's a great conclusion to this whole series that we've been doing, because I haven't really been discussing the actual original problem for most of the time here, but it's finally going to all come together. And I couldn't have done it without my trusty cup of joe. And I also couldn't have done it without the great other YouTuber, Flammable Maths. I can't recall if I've ever thanked you for promoting the first video in this series on your channel. If I didn't, because I'm too lazy to check. If I didn't, thank you so much. It's my most viewed video on the channel. It's got over 1,000 views. I really, really appreciate it. You're fantastic. Keep up die gute Scheiße. I actually made a mistake in the previous video, and I need to correct that at the beginning of this one. It's not, you know, earth-shattering. Everything that I've done so far is still completely fine, except for this little error that I said at the end that I just need to correct because it's going to rear its ugly head, as I found out when I first tried to film this video about 20 minutes ago. So here's me starting over. So let's get to it. Finally, the conclusion of this series. So, what was I able to show in the last video? I was able to show that if we consider the function that we were looking at for these last three videos, capital I, and if we only consider it at even inputs, because remember, it's 0 at odd inputs, so we don't care about that, that this, you know, this title that we've given to this integral from 0 to infinity of the natural logarithm of t to the power of 2k over 1 plus t squared dt actually has a nice closed form if we believe some very coincidental equality here. I said that this was equal to -1 to the power of k times the 2kth Euler number. But I realized I only said that because I was only looking at the coefficients of all those powers of pi over 2 that we were considering, and I forgot to write them down at the end of the video, so this is not true. What this is actually equal to is this times pi over 2 to the power of 2k plus 1. If you recall from the previous video, I had all of the coefficients, right, these numbers, times these things. But I forgot to write this at the end of the video, so I for some reason said that this was just equal to this part when it's actually equal to this whole product. So forgive the mistake, this is what I meant to say that this integral was equal to, okay? What we also can recall is that this integral from 0 to infinity is actually equal to 2 times that same integral from 0 to 1, right? All of the area under the curve from 0 to 1 is equal to the area under the curve from 1 to infinity, so we can actually write it like that. This is the correction I needed to make. It's actually equal to this product here. What we're going to do now is we're going to finally connect this to the original question at hand, which was the thing that's been on all of the thumbnails, even though it's barely appeared in any of the videos, which was capital T of x being equal to the integral from 0 to pi over 2 of the tangent of t to the power of x dt, right? And we recall that when we take the integral from 0 to pi over 2 of just the tangent of x, which means x is 1, right? The power is 1, it's actually infinity. So any power above 1 is also going to have an infinite area under the curve. So we need to make the restriction that the absolute value of x is less than 1. What we can do now is we can sort of see that it has to be related to this function, and I'll show you how. This is not going to be a proof that it's equal to this, that's actually going to be the next step after I do this part, just to show you that it is related to this. Now I really should put a question mark actually over this equal sign, because we don't know for certain that this equality holds, right? We had a very nice coincidence that all of these numbers that this evaluated to were in fact related to these numbers times powers of pi over 2. And if you recall, the Euler numbers were the coefficients of the hyperbolic and regular secant functions, depending on the alternating sign, but they're all the Euler numbers. And they're on the online encyclopedia of integer sequences. If you just type in 1, 0, 1, 0, 5, 0, 61, 0, etc., you're going to get the Euler numbers. Again, down to plus or minus sign. That's what this part is for here. So now that I've made this correction, this is actually going to mean that we can really solve this problem. So what I'm going to do now is show that this is in fact related to this, which means it's probably related to this. And we're going to see at the end of the video that it actually is, but for right now we don't know that. So I need to make a U substitution here. So we're going to let t equal the inverse tangent of u, so that when we plug this in for t, the tangent and the inverse tangent simply cancel, and we are back to just having a number to the power of x. But we can't just do that, we also have to replace dt, so we have to take the derivative of both sides, which means that dt is equal to, what's the derivative of the arctangent? It's 1 over 1 plus u squared, and we can just put the du in the numerator. And now we simply take these things and plug them into our integral, and we have to change the bounds as well. So capital T of x is now equal to the integral. So t is 0, so what do I have to plug in for u to make the arctangent 0? Well, I have to plug in 0, right? And what do I have to plug in for u to make the arctangent pi over 2? Well, the arctangent never really gets to pi over 2, but if you take the limit as x goes to infinity, positive infinity, you get that it does approach pi over 2. So it's actually the integral from 0 to infinity. And now I'm placing arctangent of u in for t. So arctangent of u is going to cancel with the tangent, and we're just going to be left with u to the power of x, divided by 1 plus u squared in the denominator times du. And would you look at that? That's looking familiar. And what we can do is, right, u is not a particularly special number. The really special number when it comes to exponentials is e. So what we're going to do is we're going to rewrite this as e to the power of x times the natural logarithm of u over 1 plus u squared du, and you may think that seems to be complicating things, but what about the exponential function is helpful here? Well, what we can do is consider its Taylor series. So we can rewrite this as the integral from 0 to infinity of the sum from k equals 0 to infinity of x times the natural logarithm of u to the power of k all over k factorial divided by 1 plus u squared du. I hope everyone's following that. All I did was take the exponential function and write the Taylor series version of it. But now what we're going to do is take everything that doesn't depend on u and just factor it out of the integral. That includes the summation, because it's got an index of k, that includes the 1 over k factorial, and that includes the x to the k power. So all of those things do not depend on u, so we can simply factor them out of the integral. And you'll see that we end up with the sum from k equals 0 to infinity of x to the power of k over k factorial times the integral from 0 to infinity of the natural logarithm of u to the power of k over 1 plus u squared du. And I know this isn't the final reveal of the video, but damn, there it is. We just showed that our question, our capital T of x, is in fact related to our function I of k. Because this is I of k, right? It doesn't matter that this variable is u, though it's improper, this is a definite integral, which means it doesn't actually matter what letter we use. T, u, cow, chicken, it doesn't matter. So this here is I of k, right? Because we haven't put an even input in, we just know that it's I of k, which is amazing, which is just amazing. We can rewrite this as the sum from k equals 0 to infinity of x to the k over k factorial times capital I of k. We have just written our integral that we've been trying to figure out for these 4 videos in terms of this thing that we've been studying for like most of the time here, which is just crazy, like we somehow tied it in. But remember, we don't really care when we put in odd values for k, because I of k is 0 when k is odd. So we can actually just consider only plugging in 2 times integers. So because this goes from 0 to infinity, we don't really have to do much adjustment. We can just change all the k's to 2k's. So x to the 2k over 2k factorial times I of 2k, which is just amazing that we can do that. Now, because this equality is not known, we can't really say for certain that this is what it's going to be equal to. If this equality is true, we can just take this and plug this into here. So this is going to be equal to the sum from k equals 0 to infinity, and I'm simply going to replace I of 2k by that equality that we have up at the top of the board, right here, involving the Euler numbers, and it's x to the 2k over 2k factorial times negative 1 to the k times the even Euler numbers times pi over 2 to the power of 2k plus 1. If this equality does in fact hold, and this question mark weren't there and we knew it were true, then it would have to equal this thing in terms of the Euler numbers. And because this is an infinite sum over the Euler numbers, this is almost certainly going to have something to do with either the hyperbolic secant function or the secant function. So let's erase this now, because this is just a hunch, right? We don't actually know that this one is true. I have to put the question mark there as well, because we haven't yet proven that it actually has something to do with the secant function. So what I'm going to do now is erase all this and actually prove that this is involved with the secant function and that this equality really does hold. So let's take a look at that now. New color time. So we're going to actually finally prove what capital T of x is equal to. Consider, oops, not I, capital T of x is equal to the integral from 0 to pi over 2 of tangent of t to the power of x dt. What I'm going to do, which may seem a little odd, but I'm going to sort of manipulate this a little bit, and I'm going to rewrite this. We know that the tangent of t is equal to sine of t divided by cosine of t, right? So I can rewrite this in that way. 1 over the cosine of t is the same as cosine, cosine of t to the negative 1 power. So I can actually rewrite this as the integral from 0 to pi over 2 of sine of t to the power of x times the cosine of t to the power of negative x, right? Because it's in the denominator and being raised to the power of x. And I'm going to make one more little adjustment to this integral here. I'm going to slightly rewrite it in a seemingly silly way, but it'll all come through. I'm going to multiply this by 2 and then multiply it by 1/2, which of course won't change the value of the function because 2 times 1/2 is just 1. So we have 1/2 times 2 times the integral from 0 to pi over 2 of the sine of t to the power of x times the cosine of t to the power of negative x times dt. Now wait a second. What is that? That is something that if you scour math YouTube channels, especially Flammable Maths, aka and used to be known as Fappable Maths, which I always got a chuckle out of, you'll recall maybe that he did a video proving that if you consider something called the beta function, which has two inputs, x and y, which is equal to, by definition, gamma of x times gamma of y over gamma of x plus y, he was able to show that this is equal to 2 times the integral from 0 to pi over 2 of the sine of t to the power of 2x minus 1 times the cosine of t to the power of 2y minus 1 dt. And if that isn't pretty much what we've got right there, isn't that neat? So if we want to write this in terms of the beta function, and therefore the gamma function, we simply need to be able to write x as 2 times something minus 1, and write negative x as 2 times something minus 1, and then we can represent it using the beta function. And that's not too difficult. So because of this relationship and this representation here, we can see that this is equal to 1/2 times 2 times the integral from 0 to pi over 2 of the sine of t to the power of, how can I write x as 2 times something minus 1? Well, it's going to be 2 times 1/2 plus x over 2, all minus 1, times the cosine of t to the power of 2 times 1/2 minus x over 2 minus 1 dt. And now that I've written x and negative x as 2 times something minus 1, this is the beta function with these as inputs. Right? Let's just make sure. 2 times 1/2 is 1, 2 times x over 2 is x. 1 plus x minus 1 is x. 2 times 1/2 is 1, 2 times negative x over 2 is negative x. 1 minus x minus 1 is negative x. So this is actually correct. And by the definition that we just had, we can see that this is 1/2 times the beta function evaluated at these two inputs. So it's equal to 1/2 times beta of 1/2 plus x over 2 and 1/2 minus x over 2, which by the definition of the beta function is equal to 1/2 times the gamma of the first input, 1/2 plus x over 2, times the gamma of the second input, which is 1/2 minus x over 2, divided by gamma of the sum of those two things, gamma of 1/2 plus x over 2 plus 1/2 minus x over 2. Now let's quickly take a look at this denominator. 1/2 plus 1/2 is 1. X over 2 minus x over 2 is 0. So this in the denominator is the same as gamma of 1. It is gamma of 1. And gamma of 1 is equal to 0 factorial, right? 1 minus 1 factorial, and 0 factorial is 1, so the denominator of this is 1. And we can actually just write this now as 1/2 times this product of gamma functions. Isn't that amazing? We've shown that our original question, this integral of powers of the tangent function, is actually equal to a product of gamma functions, which is just fantastic. But what we can do now is reference a little something. We can write this as 1/2 times the gamma function. We're going to keep this one the same, 1/2 plus x over 2. But we're going to rewrite this one as gamma of 1 minus 1/2 plus x over 2. And the reason I'm doing that is because then I can utilize something called the reflection formula. It looks like gamma of something times gamma of 1 minus that same thing. Let's make sure this is equal. 1 minus 1/2 is 1/2, and then there's the negative x over 2, right? So this input is the same as this input here. But we know of, sort of, from other people's videos, that there is such thing as the gamma reflection formula. So we can actually write this in terms of cosecant of x. So, because it's gamma of something times gamma of 1 minus that same thing, according to the gamma reflection formula, which you can feel free to look up, this is equal to 1/2 times pi times the cosecant of pi times that input there, which is 1/2 plus x over 2. So this is equal to the cosecant of this. I'm going to rewrite this a little bit. I'm going to write this as pi over 2. And I'm going to factor out this 1/2 here and write this as pi over 2. Right, so we're going to get 1 plus x in there times pi over 2. So I hope this is clear so far. I'm just using, I think it's called Euler's reflection formula. I think it's named after Euler. Every thing is named after Euler. So this is what you end up with if you apply the reflection formula for the gamma function. It isn't too hard to see, if you know your shifts and whatnot for trigonometry, that this right here is actually equal to the secant of pi over 2 times x. So we have pi over 2 times the secant of pi over 2 times x. And that's our final answer, boys and girls. The question we've been trying to answer, this integral over powers of the tangent function, this x here, if x is between -1 and 1 strictly, and this is equal to pi over 2 times the secant of pi over 2 times x, which seems like a lovely, lovely answer, and it's way simpler than I ever thought it was going to be when I first set out to try and solve this problem, pretty much like a couple months ago at this point. Obviously, I've known this answer since then, but I've been working towards it to sort of explain it to everybody. But let's not leave this conclusion here, because what were we able to show? We were able to show that our integral was also equal to that infinite sum, which involved the function capital I, which was the integrals of powers of logarithms. So let's erase all this now and relate that back to that thing there. So the secant of x is actually equal to the sum from k equals 0 to infinity of -1 to the power of k times the even Euler numbers times x to the 2k divided by 2k factorial. This is a true statement because this is sort of what the definition of what the Euler numbers are. They satisfy this relationship. They are the coefficients of these terms in the Taylor series for the secant function. In other words, the secant function is the generating function for this right here. But we didn't end up with secant of x. We ended up with pi over 2 times the secant of pi over 2 times x. So let's plug those things in. So we multiply by pi over 2, multiply by pi over 2, and now we have to plug in pi over 2 times x. So I'm going to plug in pi over 2x for x, right? So we end up with pi over 2 times the secant of pi over 2 times x, and this is equal to pi over 2 times the sum from k equals 0 to infinity of -1 to the power of k times the even Euler numbers times pi over 2 times x to the power of 2k over 2k factorial. Doing a little bit of a rearrangement, we can bring this pi over 2 on the inside, bring the pi over 2 out of that power, and look what happens. We end up with the sum from k equals 0 to infinity of x to the 2k over 2k factorial times -1 to the power of k times the even Euler numbers times pi over 2 to the power of 2k plus 1, which is exactly the sum that we had before, right? This is the sum that we had before, except this equality had a question mark over it because we didn't know that it was absolutely sure. But we've just been able to prove that the powers of the tangent function, integrals over that, were equal to this. Which means that, and because this is equal to this, that must mean that the powers of the tangent function are actually equal to this. But because we were also able to show that the powers of the tangent function, the integral, was equal to this relationship with the logarithms, which then ostensibly had to do with this, but we also came about this another way, we've actually been able to prove, this is the end of the proof, that shows that this right here does in fact equal I of 2k, which is what we were trying to show from the get-go, which if you recall, just for posterity, is the integral from 0 to infinity of the natural logarithm of t to the power of 2k over 1 plus t squared dt. So it's all come full circle. So we don't need any question mark there, it's all true. And this right here is equal to capital T of x, our original question, which was the integral from 0 to pi over 2 of the tangent of t to the power of x dt. And so we finally answered that question. It's equal to this, and it's equal to this, and it's all come together. Finally, full circle, we've solved the problem. We've been able to show that this integral over powers of the tangent function is equal to this representation involving the secant function, which must be equal to this sum involving the Euler numbers, and this term here is equal, now that we've been able to prove it in another roundabout way, to capital I, our function that we've been studying for the past 3 videos. Isn't that just beautiful? That's amazing. We've had to go down so many different paths to be able to connect all these things together, and we finally have. I'd really like to thank, again, Flammable Maths for promoting the first video of this series. I really hope you and everyone else that watches this enjoys this lovely conclusion that we've had here. And I think it would have been a little boring to just immediately jump to the beta function and get this conclusion, because I think it was really cool to see how all of these things are actually interconnected. Integrals over the powers of natural logarithm, integrals over the powers of the tangent function, Euler numbers and infinite sums, Taylor series, secant functions. It's just been wonderful. It's such a beautiful little excursion that we've gone on here, and I want to thank everybody for watching. If you've watched all 4 videos, I really appreciate it. I've got tons of other integral questions that I want to answer, and I'm definitely not going to take this long to do them. I just wanted to show all the different ways you could approach this problem, and it's just such an amazing piece of mathematics. So thank you for watching, and I'll see you in the next video.